Kim, thank you so very much. That was
Right on
just
time.
lovely.
Thank you so much.
We
Have
all
a blessed
appreciated
day.
it.
Thank you.
And I'm happy to say we could actually hear it in the auditorium this time. And I think everybody
Oh,
really enjoyed it. I see a lot of thumbs up.
oh, thank you so very much. Thank you for having me. Always a pleasure to be here.
I don't know if you could hear the applause, but you got applause.
Oh, thank you. I've got a brand new lever. I had a broken lever and it got fixed by my wonderful teacher. We had to have it shipped in. So I'm glad it worked out. Thank you.
Well, yeah, it's working fine. That's great.
Thank you.
Okay, well, welcome everyone to the January meeting, the very first meeting in 2025 for Orange County Astronomers. I'm Barbara Toy. I'm your current president, and tonight is the end of our election. So you get your chance to voice your support or otherwise for the current board. And I do hope you'll take the opportunity. And those of us who are down here in the auditorium, we actually have a voting box and we actually have some paper ballots. So if you are down here and you don't want to do the electronic thing, by all means, come down and put a ballot in the box. In an envelope. The instructions are on the ballot. And if you are let you know. Let me see. We do have a raffle tonight. I don't know how many of you guys had found out about it. That means a raffle for those of us that are here in person. And tonight is going to be a very nice eyepiece. This will be coming up after the announcements. So anybody here in the auditorium who hasn't got a ticket, let Sam know and he can get you one. Unfortunately, right now, this has been a very difficult week for many people because of the fires up in the LA area. I hope that no club members are directly affected, but we all tend to have family and friends in the vicinity. We certainly express our deep sympathy and concern for those of us that may be affected. And I hope all of you stay very safe. We have some further wind events expected in the coming week. So we're not out of the woods yet by any means. And of course, as astronomers, aside from the horrors of the fires themselves, there's also the effect of smoke on visibility conditions. So there are many reasons to pay attention, unfortunately. And let me see, with that, I think it may be time to turn it over to our beloved announcement person. Ready to go, Kyle?
Yeah. All right. Make sure I share the right thing. There we go. All right. So welcome new members. Your name badges will be on the whiteboard either this month or next month. If you're not attending the meetings in person in a couple months, those name badges will be mailed to you automatically. Please remember that coffee, donuts, and water are available for purchase up at the library entrance if you're joining us in person. Upcoming events, the next ANSYS Star Party is January 25th. Astrophysics is meeting on January 17th at Orange Coast College. The next beginners class is February 7th, and the next board meeting is January 26th online. You can find more information about all of our club events on the website. Our Adopt a Scope program is up and running. Just as a reminder, you can find more information on the website there to review a sample adoption agreement, view the inventory, and just learn more about the program. Our outreach events coordinator is Martin Christensen. Please contact him if you would like to help out at any of these upcoming outreach events. We're looking for volunteers at all of them. It's always a fun experience, so please join us and help volunteer if you're able and willing. Dave Fisher is the Serious Astronomer editor. we love to have club members share articles, images, etc. In the newsletter. So if you have any items of interest, please send those over to Dave Fisher and he will review those. Please remember that everyone does get a mailed copy automatically, but if you would like to opt out of receiving the paper copy, please let Charlie know. The newsletter is available to all members through the website. Reminder to all those who use the ANSA site, make sure the ANSA house is locked if you're the last one to leave and to close the gate to the site. Please remember to help with weed clearance throughout the property. I don't think it needs to be stayed, but we want to protect our property from fire as much as possible.
Before you go on to the next one, Charlie was reminding me that with all of the issues with the fires, we have had a number of power outages at ANZA as part of the general fire safety programs for the utility. So if you're planning to go out there, please check to make sure that there's going to be power before you you head out. Generally, we've been posting that information on the Astro Imagers and the OC Astronomers email groups. Or Charlie is usually notified, so you can check with him as well. Anyway, back to you, Kyle.
Yeah. Barbara already mentioned about the upcoming leadership elections. Please vote as it's a vote of confidence for the board to ensure that the board feels like they have the support of the club members. Even though all the races are uncontested, we always love your support. The raffle was also mentioned. That'll be coming up shortly. It's a high quality eyepiece tonight. Next month, we'll be raffling off a Celestron 8-inch Schmidt Cassegrain scope with go-to mount. You can see all the specifications there. If you would like to win this scope, come to our next meeting next month and you might be walking away with a nice telescope. The next general meeting will be Friday, February 14th, and I'll turn it over to Chris Butler for the What's Up presentation next. Thank you.
Well, actually, we were going to do the raffle before Mr. Butler gets going. Jake, you going to come up? Okay, Jake, excuse me, the thing is over there. Has everybody got a ticket? Okay, we have two more tickets that. Okay, and we will have Jake, who is the head of our Adopt a Scope program, formerly known as the Scope Loaner program, will be doing the drawing. Yes. Okay, here we have the eyepiece.
The eyepiece fits either a 1 1/4 inch slot eyepiece holder or a 2-inch. It has 2 separate rings, so it's pretty fancy, and it's worth on eBay a few $100s.
Okay. We will do the last four digits. That would be 8095. We have a winner.
Curiosity with the specs of the
14 millimeter open wide angle.
Mhm. Okay.
Take a picture. Take a picture, guys. Take a picture.
Uh,
Ladies have won the last 2 times.
Hey, that's great. Okay, well, we have a winner and we've actually taken a picture. So you may actually get to see a picture if you aren't here in person. And with that, I think it's time to go to our wonderful What's Up program with Chris Butler, the incomparable Chris Butler.
Thank you very much. Good to see you all. I do want to say I meant to be there in person tonight, but it came down with a bug. I'm sorry, I may still be contagious, so I decided to protect you all and surrender my opportunity to win that glorious eyepiece. I cannot. Next month I'm going to be there. Let me leap right into the What's Up part of the program and try not to think about that astonishing eyepiece. Oh, I would have loved to have gotten that. Let's have a look here at the What's Up for this month. All right, can you see my screen all right?
All great, thank you. And if you could just hide the notification on the bottom.
Yes. Thank you. All right, let's go ahead and jump straight through. First of all, we are past the winter solstice now, so the days are getting a little bit longer. As a coincidence, interesting coincidence, local noon, the moment that the sun is at its highest, usually does not occur right at noon for complicated reasons. However, right now, local noon is actually just about exactly noon when the sun is at the highest, noon on your watch. That's kind of a fun coincidence. But like I say, we're having a little bit more sunlight every day. Night's a little bit shorter. Looking at the moon phase, we've got a waxing crescent, meaning the moon is very bright and is visible in the east rising right now. We're swinging around towards a full moon on the 13th of the month. Good for looking at the moon. Obviously interferes with looking at some other things, but not a couple of bright planets. And we'll be talking about that in just a minute. They are bright enough, they don't care if the moon's in the neighborhood. But if you don't like the moon and you want dark skies, don't worry. We do have a last quarter moon when the moon won't rise till midnight is going to be January 21st. And then we get around to the dark of the moon on January 29th to round out the month. Running through the planets here, Mercury is a morning object. It's not perfectly placed, but it is still definitely visible, but you do have to get up at dark 30 and look in the morning. Venus is the brilliant object in the west as the sun goes down. It is at its absolute best. It was farthest from the sun, swinging to the side, elongation, as we like to say, on January 9th. It's about half lit right now. It is the brightest object in the sky, except for the moon in our night sky. Mars and Jupiter are both brilliant. We'll be talking about them more. They're both well placed. So Mars and Jupiter are leading attractions this month. Saturn is in the southwest. It is up, but not very high. I'll show you where you can look for it. It's an evening object. Uranus is very well placed, actually. So if you want to check out the seventh planet, you have binoculars or a telescope. It is well placed, and I'll show you where to find it. Neptune, evening object, but not very high in the sky as the sky gets dark, not well placed. Pluto is behind the sun, and that makes a slight diminishment in its otherwise brilliant appearance in our skies. So no, not time for Pluto right now. I mentioned Mars. We're passing Mars. Mars is going to be on January 16th. Will be just passing us on the outside track. As you may know, not all passes when we're closest to Mars are the same, because Mars is sometimes farther from the sun and sometimes closer. This is not one of the close passes. The orange box drawn around this particular opposition, as we call it, of Mars shows no, this is not one of the absolute bests, and the next one will also not be one of the absolute bests, as it was, for example, in 2018, we had a very good pass at Mars. But Mars is much larger and brighter than usual. It is definitely going to catch your eye in the sky, and you do want to look at it with the scope. This is the face of Mars we're seeing tonight, as a matter of fact, at 9 p.m. Obviously, it's not going to look this large outside of tabloid journalism. No, I mean, this is a computer graphic, but it does show that during this pass, Mars's northern hemisphere, that's the one with the cyan-colored pole at the top, north is tilted slightly towards us. It's almost an equatorial view. For the next several days, when you look at Mars in the convenient evening hours, you'll be looking at the side of Mars, which has Mariner Valley. That's the long gash across the face of Mars you see there, and the volcanoes. Now, they don't show up very well in telescopes, but that's the side of Mars we're looking at for the next several days anyway. The size of Mars in your telescope. Mars is sometimes larger or smaller, depending on whether it's a close pass or a far pass. Those are the two views of Mars you have at the right, showing Mars as being 14 arc seconds across in your telescope, or almost 26 arc seconds. That's for a close pass. Mars is 15 arc seconds right now. It is closer to the smallest possible version. If you look in the sky, you'll notice Mars, although very bright naked eye object, is not as bright as Jupiter is. And one of the reasons for that is that Jupiter appears almost 4 times the size of Mars, 4 times as big in your telescope, 48 arc seconds. Of course, this is nothing compared to the moon. The moon, 1,800 arc seconds across. These are drawn to scale, so you can see the moon appears vastly larger than any of these objects, and Mars and Jupiter are not the same size, but they're a planet size, a normal size we're used to for looking at planets through a telescope. But you know, a lot of that is the result of 3D, 3 dimensions. We can't see it when we look in the sky, but you have to remember Jupiter is way in the background. It's at 5 astronomical units, not a distance of 1.5 like Mars is. We know those numbers. What does that really mean, though? Well, if we could even out the score, make it fair, make Jupiter right now at the distance Mars was, what would that look like? It would look like this. Jupiter wouldn't be 48 arc seconds. It would be 301 arc seconds. It wouldn't be magnitude minus 3-ish. It would be magnitude minus 7-ish. It would be this incredible sight in your telescope. Imagine that. For an average telescope, Jupiter would completely fill the view in your telescope if it was at the same distance as Mars. Well, that's not fair, though, really, because if we're going to make this fair 3D comparison, let's not just move Jupiter to track number 4. Let's move Mars to track number 5 in Jupiter's place. What would Mars look like if their positions were reversed? Mars would be 2.3 arc seconds across. It would be magnitude 3 or 4-ish, depending on some factors I didn't calculate out. But Mars would be a dim naked eye object. It would be the same size in your telescope as Neptune. Forget about details. You wouldn't be able to see any cloud patterns on Mars, dusky shadings, the polar caps, forget it. Mars would be an ochre-colored tiny dot in your telescope. That's pretty wild, imagining Jupiter being so much bigger and magnificent. Maybe you don't realize just how big Jupiter really is. At this size, if Jupiter was this close, Jupiter would be 1/6 the size of the full moon in our sky. Yeah, and this could happen in some solar systems. Planets, big planets, do get this close to other planets. It wouldn't throw Earth out of its orbit. We could have had Jupiter at this kind of distance. And if we did, all these mysteries about what the planets were, they wouldn't be mysteries. Even from prehistoric times, anyone would simply have to look up and could see with their eyes the disk of Jupiter and the moons of Jupiter as they circled the planet. This idea of Earth not being the only center of rotating motion in the universe, the whole Galileo thing, that would have happened the moment a human being was able to look up at the night sky. So 3D and pushing Jupiter into the background is the only reason we didn't have all those answers to begin with. And while we're at it, pushing Mars forward into a close orbit is the only reason you're able to see any details on it at all. One other solar system business, and this is the kind of thing that makes me just about as angry as not winning a fantastic eyepiece in a raffle, which is to say comets. I have a love-hate relationship with them. There is a brilliant comet now in the inner solar system about to pass closest to the sun, a very close pass, in fact. This is Comet Atlas C2024G3, nice romantic name there. It's about to make its pass. There are speculations its brightness may go to the high negative numbers, maybe -4, -5, an incredible naked eye comet. However, the angle at which it is approaching us means it came for us from the deep southern stars, which we can't see from Southern California. It's about to whip around the sun and then immediately head back to the deep southern stars at such an angle that even if it is this amazing spectacle, in Southern California, we basically won't get a look at it at all, except with daylight interfering. The people in the far southern parts of the Earth might get a good look if the comet doesn't break up and disintegrate when it gets close to the sun. We don't know yet what's going to happen in the next week or so. But I really do feel like this is getting silly with these orbits. Every time a new comet's discovered, it's going to be amazing, and something happens. In this case, the orbit is such that we don't get a good look. Well, eventually, we are going to get to see it, and Charlie Brown will get to kick that football, but not this time. Looking at the sky right now, we have the view here toward the southwest as the sky is just getting dark. Venus, as I mentioned, brilliant in the center of the view. I mentioned Saturn wasn't too far away from Venus in the sky. It's about 7 degrees away in the sky. Again, 3D, it's way in the background. But as you can see, it's already in the southwest and getting lower. Now, tonight with the fires and the smoke, obviously, this is not a good time to be looking at Saturn. And the same thing applies to Neptune. Neptune is there, and it's not going to be really well seen in a dark sky. It's already on its way down as the evening begins. Now, that's not true, though. If we turn around and look the other way, towards the east, we've got the brilliant winter stars rising. We also have the almost full moon, the gibbous, waxing gibbous moon there. And it is close to Jupiter tonight in the constellation of Taurus. The Pleiades, famous Seven Sisters, is leading this parade of brilliant objects into the sky. We also have Mars rising there. If you give these guys a little while and let them rise up high, say by 9 o'clock, you'll have a view something like this. Jupiter, labeled in yellow, is close to the moon. Mars, labeled in orange, is in Gemini, the twins. I mentioned Uranus. If you want to hunt it down, don't forget, Uranus is over there on the Aries border with Taurus. It's very well placed at this time. In terms of stars, I've already mentioned the Pleiades star cluster is in this part of the sky, this famous Seven Sisters. The brightest star of Taurus is Aldebaran. More on that in a moment. The bright star Capella is visible in the northern part of the sky. Betelgeuse, a very orange star, by the way. You can compare it to Mars. Marks one of the shoulders of Orion, the hunter, with his famous belt just out of view, the three stars of the belt. Castor and Pollux are the two bright stars in Gemini, the twins, and Mars, much brighter than Castor and Pollux, makes a third bright object in Gemini at this time. The constellations, I've already mentioned a few of them. Aries is over where Uranus is just barely, it's on the border. Perseus is in the far north, as is Auriga, the chariot driver. Gemini, the twins, is over in the east. Orion is straddling the equator of the sky, obviously brilliant. And there are more winter stars. We don't have time to talk about them all. I'm going to focus on Taurus. Taurus the bull, one of the oldest of all the constellations. I want to mention a few things in it with a particular eye, again, to three dimensions. The three-dimensional aspect of it is something that has to do with the Milky Way. I've turned up the brightness, and the Milky Way, yes, does pass through this part of the sky, but it's not a very bright part of the Milky Way. You may not even think of this being a Milky Way constellation. It's only in the really dark skies you get to see the Milky Way in this part of the sky. This is a long exposure photograph, a very pretty one, of the constellation there with the V shape of the Hyades star cluster and the bright star Aldebaran at the center, seven sisters, the Pleiades at the top of the view. But it certainly isn't like this in the summer when we're looking toward constellations like Sagittarius with the incredible views of the Milky Way we have then. And the reason for that's simple. We're looking towards the center of the galaxy in the summer. In the wintertime, we're looking towards what we call the galactic anticenter. The anticenter is right off of the horns of the bull, and this is direction looking out of the galaxy. But you know, look on that map on the right, and you'll see that our sun's position in yellow there, we're in the middle of the galaxy in that map, looking down at the spiral arms of the galaxy. Remember that this view toward the center of the galaxy, we have just about as much galaxy outside of us as we do inside, maybe quite a bit more, in fact. So the view away from the center of the galaxy, although it's not as bright, is just as deep. There are many, many tens of thousands of light years anyway, out there in the direction of Taurus. So trying to put a little bit of 3D into this constellation now, let's see what we can see out here. Here's some objects, some particular ones that I'm going to be mentioning. Some you'll know by heart, like the Hyades star cluster, the big V-shaped star cluster, of course, the Pleiades, and so forth. The Crab Nebula is M1. That's a very famous supernova remnant. But some others you might not have immediately committed to memory. NGC 1647 is a small star cluster. I'll show that one to you. NGC 1555 is the Hines Variable Nebula, a small nebula. And up at the top are two, Semis 147 is another supernova remnant, sometimes called the Spaghetti Nebula. NGC 1514 is a planetary nebula gas shell blown off by a dying star. That's in the very far north of the constellation. I don't think I've mentioned that one before, but there'll be a picture in just a moment. But let's think about the depth looking into this constellation. How far away are these things? Well, they're not at the same distance. They're at tremendously different distances. Aldebaran is only 65 light years away. That's the bright star in this view. And then the big V shape of the Hyades star cluster is twice as far away. So we're already getting a little 3D. Then with the dashed lines around it, not at 153 light years, is the next object. This object, NGC 1555, 400 light years away. So 3 times the distance. And then even a bit farther away, the Pleiades star cluster in this beautiful deep sky long exposure photograph showing the tendrils of gas and dust around those stars. So 444, but we're not done. You could keep going deeper That planetary nebula is 1,520 light years away, so much farther away than the Pleiades. This is, 4 times the distance to the Pleiades, going deeper and back into Taurus, away from the center of the galaxy. Even farther away, the little star cluster I mentioned, NGC 1674, 1,800 light years. Here is that supernova remnant. No, it doesn't look like this to your eyes. You need a long exposure photograph to see it like this. But the Samis 147, located almost exactly in the direction of the galactic anti-center, 3,000 light years away. And notice I haven't gotten to the Crab Nebula yet. I was actually surprised how far away it was. I'd forgotten, to be honest with you. It's at 6,500 light years away. It's a long way out there, out of our spiral arm and in the next spiral arm toward the edge of the galaxy. If it helps, trying to look at the distances, we built a scale model where 1 light year was 1 inch. Aldebaran would be 5.5 feet away. The Hyades almost 13 feet away. That variable nebula, NGC 1555, be about 33 feet. The Pleiades a bit more. And then eventually getting out all the way to the Crab Nebula would be 541 feet away. So this view out into Taurus is not a flat map at all, any more than looking at Mars and Jupiter is a flat view of the sky. These objects lie at very, very different distances from us. Well, there's a little different perspective, I hope, for you on these familiar stars. Got to get out there, got to check out Jupiter, got to check out Mars right now. And I hope that will prime you for a fun start to the year in the sky. Thanks a lot.
Thank you very much, Chris, for yet another wonderful presentation. We're so happy to have you with us every time. So our speaker at this meeting is the Senior Education Specialist for Rubin Observatory and oversees the Rubin Observatory Education Program. Prior to joining Rubin Observatory, she taught physics, earth, and space sciences at the high school and college level, as well as working in planetariums and observatories. She is also a past president of the National Earth Science Teachers Association and twice past president of the Michigan Earth Science Teachers Association. Also, as a lifelong amateur astronomer, she has a personal observatory near Tucson, Arizona. Please join me in welcoming Ardis Herrold. Ardis.
Thank you, everyone. Okay to share my screen?
Yes, please.
Okay. And does that look good to you?
All great, thank you.
Okay, great. Well, first of all, thank you so much for inviting me to be with you tonight. And I just want to express my sympathy for any of you who have friends who have lost fires in the area not too far away from you. I live in Tucson, Arizona, so I'm a little bit farther away, but certainly do understand what happens with wildfires in Arizona as well. So um, I appreciate all of the help that people are giving, but it's just, wow, isn't it just a mind-blowing thing about what's happening? So I wanted to talk to you tonight a little bit about an observatory that many people have never heard of. Hopefully some of you in the audience have. And that is Vera C. Rubin Observatory. And I'm going to tell you now why this telescope is so unique and so different from anything that we have currently on the surface of the Earth. And you'll be hearing a lot more about Rubin Observatory in about a half a year from now when we have our first light. So you'll have kind of the sneak preview and maybe be able to tell people a little bit more about Rubin before everybody else hears about it in the press. And so the other thing I wanted to just mention is that I certainly will be happy to take your questions afterwards. I'm not sure, based on, coming to your club, what your interests are, what your astronomy levels are. So I'm kind of aiming for the middle of the road here, assuming you all know some astronomy, but maybe not a lot of astronomy. But I'm going to start by just telling you where our observatory is. Although the headquarters for Rubin Observatory is in Tucson, Arizona, because it is a US-funded telescope, its physical location is in Cerro Pachon, Chile. And if any of you are familiar with Chile, that is not too far away from La Serena, which is a seaside town, which is north of Santiago. Now, our telescope is not too far away from some of the other telescopes that are in our US installation of telescopes in Chile. We're not too far away from Gemini South, from SOAR, and from the Cerro Tololo Inter-American Observatory. So if any of you have been to Chile, or are you familiar with some of those other telescopes, we're kind of like on the next ridge over from them, just a very short distance away. You can see that our latitude is about 30 degrees south. So I'm not exactly sure what your latitude is, but it's almost the flip of the equator, right? So the latitude of the observatory is about as far south as we are north of the equator. And the altitude is not really, really high. We're on kind of like the foothills of the Andes Mountains. But you can see there that we're at almost 9,000 feet. So that puts us significantly above most of the clouds, and certainly a thinner layer of air. For those of you who are not really familiar with how our optical telescopes are organized in the United States, all NSF-funded telescopes that are either optical or infrared are under the umbrella of what is called NOIR Lab, the NSF, National Optical Infrared Astronomy Research Laboratory. It's quite a mouthful. But NOIR Lab is an organization of which Rubin is a part. And so this incorporates a lot of different telescopes from around the country. Maybe some of you have visited some of them. The telescopes in Hawaii, DKIST and Gemini North. Very near Tucson here, we have Kitt Peak National Observatory. And we also have a number of observatories, as I mentioned, in Chile. And even things like the Space Telescope Science Institute, Webb, Hubble, these are all related to NOIR Lab, but they're in a different umbrella organization just because they're in space. So this graphic kind of gives you the overview of all of our nationally funded observatories. And of course, not all of them are in the Northern Hemisphere, and good reason for that. So as you might know, we put observatories on mountaintops, not only to get above the clouds and the weather and the light pollution somewhat, but also the thinner the layer of air we have to look through, the less turbulence or the twinkling of the stars we get. So the air high on mountain ridges like this is very stable. And here, being very close to the Atacama Desert in Chile, we have some of the highest, driest, most stable air on Earth. And at the same time, we don't want observatories too far away from cities and infrastructure, because we need people who will come live or come work at the observatories. And, they have to live somewhere. We also have to have support facilities that, for instance, La Serena, which is about a 2-hour drive from the observatory, is a major shipping port. So in order to get materials back and forth, we need the infrastructure of cities somewhere nearby. And so we're in a very good place for observing. And this is a more recent picture of what our observatory looks like right now. I'm going to tell you the story of how this telescope came to be, just briefly. And I will mention that for those of you who do not know, and I haven't said that yet, Our telescope is not yet operational. It will be later this year. So we're very, very close to being totally complete. But the origin of this telescope started all the way back in 1996. So if you think about that, that's, 30 years ago. And what was going on then is Tony Tyson of UC Davis wanted to have some kind of instrument, telescope, that could do a large survey of the sky to explore for dark matter. He realized that we didn't have any capable instrument at that time that could survey enough of the universe quickly enough to gain a better understanding of dark matter. And at about the same time, Roger Angel from the University of Arizona was thinking about what kind of telescope could be designed that would create this very large field view every time it took an exposure. And this is exactly what kind of Tyson was imagining that he would need. And so together, this began conversations about what we call the dark matter telescope. And so why do we want to build that telescope, which is now what we call Rubin Observatory? Well, as you probably know, most of the universe that's out there is not visible to us. And even the parts of the universe that we think we know about, like dark matter, we're not really sure its entire true nature. And then it gets even more mysterious when you factor in things like dark energy, which we're using to explain why the universe is accelerating its expansion. And so we really do need a telescope that will start giving us data at a faster rate and a deeper rate to help understand what's going on with dark matter. But this dark matter telescope can be used for other kinds of science too. Every 10 years, we have what's called the decadal survey in astronomy and physics. And we put together what we feel are the highest priorities as a country for scientific research. In 2000, this telescope was named in that decadal survey, but it was not at the very top of the list yet. At that point, it was renamed the Large Aperture Synoptic Survey Telescope, LSST, to highlight the three aspects of what this telescope would be like: a wide field of view, very quick ability to scan the sky, and the ability to see very faint objects. So no telescope previous to this have ever put together all three of these qualities on the same scale. In 2015, we began construction, so that's been 10 years. And in 2019, it was renamed Vera C. Rubin Observatory. Some of you might know that Dr. Rubin was responsible for providing convincing evidence that, in fact, a lot of the universe is in the form of dark matter. She did research for decades that showed that the stars, as you move out from the galactic centers, are not moving slower around the galaxy as we might expect, but in fact are maintaining a relatively constant rotational velocity around the galaxy. Now, Rubin did not come up with the idea of dark matter that had been tossed around for decades before, but there really wasn't very much convincing evidence for it. And the astronomy community as a whole wasn't really buying into it until Rubin came on the scene and provided, survey after research project that showed consistent results with her work on galaxies. So one of the reasons we felt that it would be incredibly great to name this observatory after Rubin was that she was the person who really pushed this dark matter research to the forefront. But beyond that, Rubin became an astronomer at a time when it was very difficult for a woman to get into astronomy as a career. She was discouraged all the way along in her studies. She was prevented from doing research at observatories because she was a woman in the earlier days. And so we felt it was a great honor for us to name this is the first observatory, major public American observatory, named after a woman scientist, and we felt it was entirely appropriate to name it after Vera Rubin. Now, even though Rubin was passed over for the Nobel Prize, she did get a lot of other awards and accolades during her life. And now, if you look around, you'll find out that, she's commemorized on the moon and Mars. And this year, in 2025, there's a series of quarters coming out, famous American women, and she's going to be one of the 4 people featured on quarters. We don't know exactly what month they'll show up, but look for Rubin on a quarter pretty soon. And did you know that there was a Verubin Nebula in Star Trek Discovery Season 3? So, I mean, her name has been tossed around for a long time. Um, Even though very few people have ever heard of her, she really is a noteworthy scientist. So let's talk a little bit about the design of Rubin Observatory. This is a picture from October, and you can see comet A3 Tushinshin Atlas there, and also Venus. So we're looking toward the west. You see that Rubin has a very unusual shape. It's built into the mountain, and it's oriented to take advantage of the prevailing winds. So the winds are providing the least turbulence as they flow over that dome, and also we're maximizing the ability of that wind to ventilate the observatory at the same time. When you look at a cutaway view of Rubin Observatory, the reason it has that sort of unusual shoe-shaped figure is that we've built all of our facilities right at the dome. And this is an incredible savings of cost and energy efficiency for us, because many telescopes, for instance, when we have to get the mirror resilvered every so many years, it has to be taken out, it has to be trucked somewhere to a place where we can recoat the mirror. Everything is right here. We don't have to take the telescope, the instrumentation, very far at all if it needs any work or any maintenance. So you can see there's a machine shop, the control rooms are here. There's a very large area on the floor where we can have like maintenance facility and storage. There's a chamber there to silver the mirror. And then the other part of this building is a hoist to then come up to the observatory where you can see the telescope itself and its pier. If you look on the main floor of Rubin Observatory, that's kind of like in the middle of that shoe-shaped structure. This is kind of a view of what you might see on a typical day. Now, because we're still in the construction phase, you can see some parts of the observatory here. This is the secondary mirror that is not in the telescope at this particular point. We've got a commissioning camera. And here's a picture of the control rooms as we go on. And then in the dome itself is the telescope. And in October, we dedicated this telescope and gave it the name the Simony Survey Telescope. The observatory is called Rubin Observatory. The telescope is called the Simony Survey Telescope. And that is named after the Simony family, who in the very beginning of construction donated $30 million to begin to make the large primary mirror. By the way, Bill Gates chipped in another 10 million. So this telescope is not entirely funded by the government, but it got a great kickstart from private donors who really believed in the concept. One of the things you might notice about this telescope right away is it looks incredibly short and squat. And we like to think about that as being short and nimble. This unusual optical design, which I'm going to tell you about, has allowed us to make this telescope very short in size. That makes it lightweight, that makes it able to move very quickly on sky. And it also means that we didn't have to build as large of a dome for it, because the telescope itself is very compact. Something else that's interesting about the telescope is it has a super wide slit compared to most domes. And that's because this telescope will be taking an image every 30 seconds on sky. And it will do this all night long every night that it's in operation for 10 years. So we'll talk a little bit more about the survey itself, but because the telescope has to move very quickly from one exposure to the next, all exposures being 30 seconds, the dome is constantly in motion. It's what we call a crawling dome. And the slit is very wide, so as the exposure starts on one edge of the slit, by the time the exposure is over, we're at the other edge of the slit, and the dome has crawled into position for the next exposure to happen. So it's a really kind of an unusual thing. And the telescope mirror itself, as many of the large modern mirrors, are made of a honeycomb structure, which makes it relatively lightweight. This is a picture of the primary mirror when it was finished at the mirror lab at the University of Arizona, the Keras Mirror Lab. And you can see that it's a pretty large mirror. It's 8.4 meters across. Why 8.4 meters? We have a tunnel that we have to get through to go from the sea, where the mirror gets shipped, up to the mountain. And that tunnel cannot fit anything larger than this 8.4 meter mirror. You can see this is the night we were bringing it through, and there are literally just inches on either side of the tunnel as we are bringing the mirror up the mountain. Now, this mirror has an unusual optical design. It's not just a simple reflector. The primary mirror actually has two different curvatures to it. The outer mirror has less curvature, the inner a little bit more. We call that outer mirror M1, the primary mirror, and then the inner one M3 because it's the third reflecting surface. So as you can see in this animation, the light is coming in from space, striking mirror 1, reflecting up to mirror 2, reflecting down to mirror 3, and then bouncing up into our camera through a series of lenses. Both the M1, M3 mirror and the M2 mirror have active optics applied to them, so we can make small adjustments due to gravity or atmospheric conditions. This is a picture of M1, M3 just before installation. And I wanted you to just take a minute to look at that because it's kind of freaky weird when you look at it. So we have the outer surface, which has less curvature. And then we have the inner surface, which is the M3. And then this person is standing in the hole in the middle of the mirror. But you can see some really cool physics there in terms of the reflections and how they change with the mirror. I wanted to talk a little bit about coating the mirror. So this is at Rubin Observatory in the coating chamber. And I'd like to show a short video about this mirror as it was coated. So I just wanted to mention something about that mirror. The total amount of silver in the coating of that mirror, if you put it together, would be about the size of a cherry tomato. So a very, very thin coat that we're looking at on that mirror. Let's talk a little bit about the camera. We have the largest camera ever built for astronomy in the world. It's the size of a Mini Cooper. It operates at minus 100 Celsius and weighs 3 tons. So this is a picture of the camera that is at the observatory now, awaiting installation on the telescope. We call it the LSST cam for short. You'll recall that LSST was an acronym for the Large Synoptic Survey Telescope, the previous name of the observatory before we changed its name to Rubin Observatory. Now, this camera uh, has two world records, Guinness World Records, one for the largest optical lens, so you can see how big that is in relation to a person there. And also, it has the highest resolution camera ever built for this kind of work, 3.2 gigapixels. And so, as you can see here, if you imagine every person as a pixel, 3.2 gigapixels is like combining the population of India, China, and the US together. So a lot of pixels compared to our cameras, right? The camera will have an image set in it, 6 different filters that will image the sky from ultraviolet to near infrared. And so you can see the size of one of those filters there, and it will have a filter changer in it, so the filters can be changed very, very quickly. Typically, in one night, we'll be going through a series of 2 different filters for each object, and then the next visit, we'll go through 2 different filters, and then by the third visit, we will get all 6 filters in for these objects. Every object is visited twice a night, so we can do 2 filters per night. Now, this camera produces images that are incredibly wide compared to most telescopes. So most of you being in an astronomy club, I'm sure are familiar with Orion. And you can see here that if you put one image on the sky from our telescope, our camera, it will be just a little bit wider than Orion's belt. So another way to think about it is it covers the area of 45 full moons. So these images are just incredibly large compared to other images from most telescopes. And that's where we come up with that first word, wide. Wide, fast, deep. This is what we are noted for. Now, because these images are wide, we can cover the sky very quickly. So every 2 to 3 nights, we will image the entire sky available from our location in Chile. Now, we won't be able to get the far northern part of the sky, of course, but we will get beyond the equator up to a little bit further to the north. And because these images are so much larger than similar telescopes, what we do in 10 years would take 1,000 for other telescopes. And so what we're really doing here is we're going to speed up history. Now think about what kind of device would you need to display an image that's 3.2 gigapixels at full resolution. So imagine you had a 4K HD TV. You would need 378 of them stacked together to look at just one image at the full resolution. Or another way to think about that is you would need a TV monitor that's a little bit larger than half of a basketball court. And so these are not the kind of images where you're going to download them on your computer and look at them, at least not at full resolution. How does it compare to your camera? Well, I think some of the high-end cameras now that are out in cell phones are what, 48 megapixels, maybe a little bit higher. But our camera, 3,200 megapixels. So this is just mind-blowing in terms of the amount of data we're going to be collecting and the sensitivity of this camera. Now, because we have this very, very high resolution, what it's going to allow us to do is see very deep into the universe. And deep doesn't always mean far. It could mean far if you're looking for faint, faraway galaxies. But deep could also mean, like you see in this picture, very faint intra-cluster light around galaxy clusters. It could also mean looking at an extremely faint near-Earth object that has not been previously detected because it was so dim. So seeing deep is really more like seeing dim, whether those objects are close or far away. And then finally, fast. As I mentioned before, in 3 nights, we can go through the entire universe. And this is a short video of watching the telescope move. And you can see in this video, and this is not speeded up. This is about how fast the telescope mount was moving when it was tested after it was built. Certainly will move at that same speed, fully assembled. So in 5 seconds, it needs to slew from one object location to another, settle, maybe change filters, so that 8 seconds later, it's ready to go on its next image. So what does this all mean? If you put wide, fast, and deep together, it's going to give us an unprecedented view of our universe, the part of the universe we can see from Chile. There's a pilot project out called the Deep Lens Survey that's trying to simulate what the sky would look like with a Rubin image. But these simulations fall far short of what we're going to see in a few short months, images that will see even deeper into the universe. And because we're constantly looking at the sky over and over again, we will detect more changes in the sky than most telescopes would ever hope to see. 10 million changes in the sky per night is the prediction. We'll have 10 million alerts per night. And those changes in the sky could be things that are changing in brightness, or they could be objects that are changing in position. Over 10 years, we will co-add these images together, ultimately producing the most mind-blowing multicolor video of the dynamic universe you will ever have seen. And so not only is Rubin strong in terms of looking for dark matter, but we're very, very strong in being able to see changes in the sky, in the universe. And that's going to be relevant to many different areas of science. So how does this translate to data? 20 terabytes of data every night. You would need 40 laptops to store 1 night's worth of data. We are changing the paradigm here. Astronomers are not going to typically download data. They will work with data in the cloud. They will mine data from catalogs. But, the idea of you're going to download an image and work on it over time, it's just not incredibly practical. Another way to think about that is some of you who are here are more than 50 years old. So I want you to think back 50 years ago to however old you were and where you were and what you were doing. Imagine that from that point until tonight, you were constantly listening to Spotify. No break. That's how much data is in 1 night. Or let's say you're binge watching Netflix, no break for 3 years. That's 1 night of data. So over the end of this survey, we're going to produce huge amounts of data. As you see here, 60 petabytes of data and more than 2 million images. Another way to put it in context is in the first week of operation, we'll generate more data than Hubble has ever collected. Or it would take 120 years of Hubble observing time to capture what we will capture in 3 nights. Now, this data comes from the mountain down to a base location, base station in La Serena. And from La Serena, Chile, there is a redundant structure where it gets transferred across the ocean and continents by fiber optic cables into Florida, and then goes to our data processing facility in Menlo Park, California, SLAC, and the Stanford Linear Accelerator Laboratory. And SLAC is the place where alerts will be generated. So this will all happen in less than 1 minute after image acquisition. Now, in addition to SLAC, we have data that is being stored and processed in France and in the United Kingdom. So this is really a global effort to keep all of our data together. And our headquarters for all of this is in Tucson, Arizona. So what are we going to do with this data? We are conducting what we call the Legacy Survey of Space and Time. You'll notice this is LSST. When we changed the name of our telescope, we kept the acronym and we reapplied it to the survey. And so what we're going to be doing is, for 10 years in a row, surveying the entire southern sky with 6 different filters. And you can see here that we will get, over 10 years, about 800 visits of these multicolored fields. And then we can stack them together. We can play them like a movie. But over that time, we're going to detect 38 billion objects. And that is going to produce huge numbers of catalogs. As you can see here, many more times objects than we have people on Earth. Also, I wanted to mention that these objects are both near and far. So we're going to be detecting a lot of things in the solar system as well as, beyond the galaxy. So why are surveys so important? They've been around for a long time. I just wanted to mention a few things. Sometimes you can't see a pattern unless you look at something long-term or in large scale. And that's why surveys can really help give us insights into and new ideas about our science in ways that just individual studies of random parts of the sky can't do. Also, the more often we observe the same parts of the sky, the more changes we detect. Our survey will be open to everyone. Our data becomes publicly accessible 2 years after we acquire it. In the first 2 years, all countries with data rights will have rights to that data before the rest of the world, but ultimately it will be publicly accessible for everybody. Another way to think about it is, imagine you're working a jigsaw puzzle and you have only maybe 10% of it done. This is a picture I found on the web that only sells James Webb's space images for jigsaw puzzles. And I'm hoping that in a couple years, they'll start throwing some of our images in there too. But imagine that Rubin is going to push this puzzle from being maybe 10% done to maybe 60, 70% done. Now suddenly you begin to see things that you never could have seen before. And that's why this is really, really exciting to so many people. How we're going to survey the sky is not just going up and down, and I thought you might enjoy this because it is relatively complex how we do this. But if you look at this sky survey, first of all, on the left-hand side, you'll notice this is what year it is, what night it is, what hour it is. You can see the sky rotating on these maps. And what you're looking at with that little crazy spinning little dot is images being generated. Remember, 1 every 30 seconds. The color of that dot represents the color of one of these filters here. When the moon is new, we can use filters like ultraviolet, which are not optimized for when the moon is out in the sky. So we have different schemes for filters depending on the phase of the moon. We also have to think about other things that are happening in the sky, of course, as well. This algorithm can be changed at any time so that it can be used to avoid, for instance, parts of clouds, or if there's some kind of other kind of interference in the sky, it can be changed very quickly within a few minutes. And then over time, you'll see that as we build up, looking at the sky in different filters and going back and changing the filter, over time, we'll build up that multicolor map of the universe I was telling you about. The right-hand side shows how many images are being taken in what parts of the sky. You'll see there's different densities for the images. We, for instance, will not be taking as many images right along the galactic plane as we will in the parts of the sky that are away from the galactic plane. You'll also notice there are some areas that have dark blue in them. These are what we call mini surveys or deep drilling points. These are places where we're going to take more images than the typical number of visits. We can really watch this thing for hours, but I'm not going to spend that much time on it, just to say that it is an algorithm that has been well thought out and actually had been discussed by scientists around the world, so that we can come to compromises so that everybody's science, I guess I'm going to have to hit this twice and get out of here. So everybody's science gets some time. So in the beginning, we had talked about this being the dark matter telescope. And I also mentioned that we're going to be cataloging a lot of new solar system objects. But we really have four pillars of science that many, many people around the world will do their research organized around these four pillars. So the transient sky, the things that are changing in the sky, are another one. And then lastly, the one I haven't talked about too much is the Milky Way structure and formation. So we're going to get a lot more stars than we ever have seen before in the Milky Way. We're going to be able to map out not only our galaxy, but our local area galaxies and even the galaxies that are close to us. Dark matter and dark energy, one of our big things is we're going to be able to use gravitational lensing with, I think the number is 20 billion more galaxies than we've ever detected before. Once we can map out these galaxies and where they are and find gravitational lenses in many of these areas of the sky, we can better start to understand that nature of dark matter. In the Milky Way, we'll be detecting many stars, main sequence stars that have not been detected before across the entire spectrum of all the main sequence stars, including quite a few brown dwarfs and white dwarfs and red dwarfs that are hard for other telescopes to find. So having this more complete census of stars in the Milky Way will help us with understanding models for galaxy evolution and formation, as well as just how the chemistry, the metallicity of the stars change across the Milky Way, which we'll be able to do that because by photographing every star in 6 different filters, we in effect create a spectrum of that star's light, and we can do some classifications on its metallicity. And then the changes in the universe, we are expecting on the order of 2,700 supernova detections per night. Now, if you imagine that over the course of 10 years, we'll get about 1 million supernova detections. And that's just supernovae. That's not anything else that's changing in the sky, like seeing asteroids move or looking at variable stars or changes in light from other objects like galaxies. In the solar system, this chart should be interesting to you to compare how many objects we currently know about to how many objects we expect to know about. And many of these discoveries will happen in the first 3 years or so of the solar system. So one of the interesting things that has been in the news lately is that this telescope is going to be an optimal telescope to detect that planet 9 if it's really out there. And in fact, there was just an article in Scientific American last month about that. So if you get that magazine, you might look this up and read about being on the brink of finding planet 9 if it's there. Finally, one of the things we'll be doing is working with all sorts of other telescopes to do what we call multi-messenger science. That's the idea that, we're only looking at the universe in optical, infrared, and ultraviolet light when we use the Rubin observatory. But there are other telescopes and observatories that are studying gamma rays, they're studying X-rays, and the other forms of energy and particles that are coming in from space. By combining all of these telescopes to study a certain object, we learn a lot more about it. It's just like if you know a person in one context, and that's the only way you know them. Maybe there's a person who comes to your astronomy club meeting every month, and the only time you ever see them is that, and the only thing you know about them is maybe some things about astronomy. Then you might bump into them somewhere else, and you find out, oh, they're a musician, or this is what they do for a living, and you see another aspect of them. And so this multi-messenger science, very popular idea of working with all different instruments to get a complete picture of objects that we study. And finally, targets of opportunity. What happens if another telescope somewhere detects something and they want us to look at it? An example, what if LIGO detects a gravitational wave event and we can quickly pivot to look at that area of the sky to see if in fact there's an optical counterpart to that gravitational wave, or turn it around. What happens when we detect something really unusual and weird and we put it out there as an alert? All telescopes of the world can look at that and immediately go to study it. Finally, one of the things that scientists are most excited about are the things that they call unknown unknowns. Discovery of objects we've never seen before and we don't know what they are. Maybe we're going to find that the data produced by this telescope will completely blow apart our ideas about dark energy or dark matter, or maybe support them. But certainly what we can be sure is that for generations of astronomers, this telescope is going to provide data and help them formulate questions that we don't yet know how to ask because we don't know what to ask about. So let me end up here by just telling you where we are in our status. And I wanted to tell you that right now we're in commissioning phase, which means, the telescope has been together for a while. We had a small camera on the telescope called the commissioning camera, ComCam. It was on the telescope this fall for 7 weeks. It did very well, actually exceeded our expectations for our first engineering test images of the whole system. Over the end of last month, we took ComCam off of the telescope, and now we're preparing to put the main camera on, the LSST camera. But believe it or not, that takes like about 3 months to get it done. There's a lot of things to reconfigure, hook up, and then it's quite a long time to cool it. So what we're looking at right now, assuming we stay to schedule, is that we're going to get our first image from the main camera in April of this year. And that means that a couple months after that, we will have what we call first look, or what other telescopes have called first light. And we'll talk about that in a minute. Right now, could happen as early as the beginning of June or the middle of July. Now, that's not the end of commissioning. That's just when we put those first images out to the public and to the scientific community to celebrate. After that, we still need a period of commissioning to fine-tune the system. We will begin operations and the survey at the very end of this year. And then we'll collect 6 months of data. We'll process that data for 6 months. Our first data release of an entire catalog with everything from the first 6 months will happen about a year later in late 2026. So what happens at first look? This is our first reveal of the science quality images for the world to see. You might remember not too long ago, JWST, the Webb telescope, had its first light, where you saw the first images come off the telescope. It's a time to celebrate. We've been working a long time on this telescope, and thousands of people around the world have been working on it too. There have been 29 countries working to put this telescope together, to build its software and all of its instrumentation. And so this is really going to be a global celebration. But it's not the start of the survey. So it's not like, the next day after first look, you can go collect data or get data off of the science platform. It won't be there then. And the other thing I wanted to mention to you is, what do you expect to see? So here was one of Hubble's first pictures. Here's one of Webb's first pictures. When you look at Rubin, are you expecting to see something like that, even prettier? But one of the things I have to caution you about is that we are a ground-based telescope. These two telescopes are space-based. They don't ever have to deal with atmosphere or phase of the moon or anything like that. So Rubin's images are not going to be better than Webb's images or Hubble's. We'll get more of them. We'll get deep. We'll get a lot of interesting things that we see changing, but they aren't necessarily going to be just prettier. And unfortunately, a lot of people, when they hear about, something like the first light of a telescope in the press, all they fixate on is, well, where's the picture and how pretty is it? And really, we don't care so much about that. We care about the science. And so I'm going to put this in a different context for you. So here's the starts of some well-known telescopes, right? I gave Hubble a little adjustment because we had a tiny mirror problem for a while. Here's the starts of some big things. The internet started in 83. First iPhone around 27. Google, 1998. If you were alive in 1998 and you heard about Google, it didn't really impress you in the very beginning. You were like, you didn't really know how it would change the world, right? When you heard about smartphones, were you quick to change? Or were you one of those people who said, hey, all I need is something to make calls? But if we think about things like the internet, Google, smartphones, Amazon, how things have changed in our world, we didn't realize at the very beginning what would happen. It was only over time we saw things change because of those inventions. And that's the perspective I'm going to give you on Rubin. It's not going to be the first day that is going to blow your mind away. It's going to be what happens after a few years. And so I want to stop here and say, get ready, prepare yourself. It's going to be fun. And thanks very much.
Wow, wow. Thank you very much, Ardis. What a great presentation, and also a great telescope. So we are now in the questions time. I'm sure there are going to be a lot of them. So let's start with the people on the ground. Doc, Barbara, do you have anything to start off with?
Question?
Yeah.
Any questions? Yes. I'm sorry, about the North Cloud? Oort cloud. The question is whether the Rubin would be able to do any mapping on the Oort cloud.
Yeah, we will definitely see objects out to, that's a good question. I don't know the answer. I know we will see objects out into the Kuiper belt easily. And in fact, one of the things our telescope will be optimized to do is find some of those very large planet-like objects that might be really far out, right? Oort cloud, I'm not sure. Good question.
Another question?
Yeah, I was thinking about a comparison again. When the Rubin comes on, will it be like the difference of when the 100-inch Mount Wilson telescope came online? It got to be used. Some magnitude of change like that, or the 200-inch Hale?
I think it'll be beyond that. And I think what the big difference is not only are we going to get these big images, but we're going to get so many so quickly that that's what I said earlier. We are going to speed up history, literally. I mean, it's kind of in my mind how the internet has changed my life. I mean, when I was in high school, I was still using a slide rule. We didn't have, computers. We didn't have internet. We had to talk to each other, actually. There was no email, all that stuff. And I think about how life has changed since I've been in high school, and that certainly isn't probably different from many other generations in history. But um, I think we've had a speed up of progress because we've been able to communicate with each other better through the internet, because we've been able to globally accumulate and share knowledge. And I think that's what we're going to see here too. We have thousands of scientists who are really ready to dig in and collaborate. And that's another thing I wanted to mention about Vera. Vera was really an advocate for not only women in astronomy who struggled to get into the field, but also young career scientists who often were ignored and treated not well. She was very inclusive. She was inclusive before that became a thing. And so we have certainly embraced her spirit, and that's why we want to make this accessible to everyone. I work in the education department. We have investigations that will use data from Rubin that we've designed. Certainly, we're going to have citizen science projects. We're going to have all those things once the data starts coming in. So there will be ways for astronomers at any level, whether you're an amateur, whether you're just a science interested person, a student in high school, there'll be ways for you to get involved.
Great, thank you very much. Let's take a few questions from the online audience. There are a couple of questions about the satellites problem. So Starlink and other satellite constructions, how obstructive or problematic are they going to be? Are there any remedies?
Yeah, let me share my screen because I'd like to go back to a slide. I get this question a lot, so I anticipated that someone would probably ask it. So here is satellite impact, like current Starlink. Look at the middle. This is kind of like the streak it makes through an image. Blue Walker 3 pretty much obliterates an image. What we'd like to do is get the industry standard to something like on the left. Now, we have been working with different satellite companies already, but I have to say, there's no control. I mean, no one can control what private enterprise does. We can make suggestions. We can try to convince them it's an important thing, but we have made some changes, mitigation with the satellite companies, for instance, putting less reflective coatings on them, changing how they rotate and the angle at which they rotate, and changing how much time they spend in low Earth orbit, which is where we have, the biggest problem. But on our end, we can also make changes. We can dither images so that, and we can collect a lot of images of one part of the sky. So even though you get a satellite trail blazing through one image, it doesn't destroy every single image you have of the sky. We also have software that can kind of reduce and remove images. Of course, we're going to reduce and remove data too. And the reality is that there are more and more satellites coming. There are more and more companies interested in launching many satellites into orbit. And so we're just going to have to deal with them like every other observatory has to deal with them. Now, I will say that if you're not familiar with this, the International Astronomical Union has a Center for Dark and Quiet Skies that has been established. And that's for the protection not only of the optical sky, but also the radio sky. from satellite constellation interference. They work with everyone around the world to understand what the problems are with the companies who try to work collaboratively on problem solving this. But I encourage you, if you haven't checked this out, to go there and see what they're doing. And, just give you a perspective. I don't know how many of you are in, what's it called now? Dark Sky Association. But I was one of the charter members of IDA. And at the time when IDA started with David Crawford and Tim Hunter in Arizona, light pollution wasn't a thing that people talked about, right? I mean, they just didn't. And they started an effort that actually now has spread across the entire world. And there are many different, organizations and industries that have involved themselves in trying to reduce the amount of light pollution for many different reasons, right? So I think we can make a change, but I don't think we're going to make it go away.
Okay, thank you. Now let's talk a little bit about the construction of the mirror. So it's built somewhere else, but it's coated and maintained on site, as opposed to many other telescopes we need to take down their mirror. Now, one of the things that you mentioned is that it's 8.4 meters because of that tunnel. This is the question that a lot of ordinary people want to know. Could not that mirror be airlifted or transported by some other means to prevent that?
I don't know if it could physically be airlifted. I know we never even considered it because it wasn't safe. So it was taken by a truck to Houston, and it was shipped out of the port of Houston through the canal and ended up in La Serena, and then it was trucked up the mountain from there. Now, we did fly the camera there, but I'm wondering if the mirror was just too heavy. I don't know what the weight of the mirror is. Too heavy, too big, I'm not sure.
Okay, and if the tunnel was not the constricting factor, how large would the scientists have gone, or how much larger we could have gone?
I don't know. That's a very good question. We aren't building mirrors, single mirrors, much larger than 8.5 meters. Um, Originally it was designed as a 6.5 meter, and I think because other telescopes were on the mountain and they were larger, and we could go to the 8-meter class telescope, we did. But we are building a lot of large telescopes around the world now that are going to be segmented mirrors, right? That work together. But I don't know what the largest mirror of the world is right now. I don't know if there's one larger than, I don't know, 8.5 meters. Does anyone know about a larger mirror than that? That's kind of at the top end of the single class mirrors now.
Okay, great. Thank you. You also mentioned about the data and also the matter of transferring it. And you mentioned about it being transferred to multiple locations, collaborators on the Earth. And you mentioned fiber optics. I was wondering if those are dedicated fiber optics or just the general internet that everybody has
No,
access.
they're dedicated. Yeah, they're dedicated redundant systems.
Okay, great. And we have another question about, you mentioned a lot of areas of astronomy that are going to be impacted by the telescope. How about exoplanets?
That's a good question. So early on, it was thought that this telescope probably wouldn't be optimized for exoplanets. But we have heard from a number of exoplanet scientists that they think, in fact, they can use our data. It's not going to be the optimal instrument, but there are a number of people who think they might be able to use our data. And I don't know much more about the science other than to tell you that. One thing I can tell you that's a little different about Rubin compared to some of the other larger telescopes that you're familiar with is that we don't collect spectroscopy in the same way that many telescopes do. There's no spectroscope on Rubin. So we can create a spectrum from the photometry and the 6 filters. And we can get a crude spectrum that is within 2% of what an actual spectrograph would produce. So for all intents and purposes, if we want to do like a galaxy redshift, we're good. It's going to work great. It becomes a problem when you have, you know, I don't know how many thousands or maybe a million objects in a picture. You can't really do spectra of very faint objects all over the place like that very quickly, you know, because our images are all 30-second snaps. And so spectra usually require a little bit more integration time, you know, to build up the light. And so what we have is what's called a photometric spectrum, as opposed to a spectroscopic light curve.
Okay, great, thank you. And you mentioned that there's going to be an image every 30 seconds. So can you tell us about the exposure time? So it's like 20 seconds is the exposure time, or is it fixed for every image? How's that calculated and how does it vary?
It doesn't vary. It's 30 seconds for every image. And with there's an 8-second time for the camera to move to the next place, slew, settle, and download that data. So it really literally is using a few seconds to download the data, and every image is 30 seconds.
Okay, thank you. Barbara, and in-person questions?
Yeah, yes. The question is, where are you getting the computer power to deal with all that data? And are you planning to use AI to help process any of it?
I don't know a lot about the AI, although I know that they have used AI a lot in training machine learning algorithms. So the machine learning is the part where, let's say we have a picture, and that picture has, I don't know, I'm going to make up a number, 50,000 objects in it. Machine learning will take that image and identify what each of those things are, produce photometry for it in every wavelength, you know. We will produce these vast catalogs of data that will be done by machine learning. It certainly isn't going to be done by people. Also, I haven't talked about brokers, but the data is actually a very complicated process. We are using the cloud to store the data, but we also have these large dedicated computing centers at SLAC, at IN2P3 in France, in the United Kingdom. And we've split up the data load, you know, so there will be processing and storage of data in these different places. But getting back to, could you repeat the first part of your question? Where are we storing it? We have it in the cloud. We have it in these computing facilities. And then are we using AI? Was that it?
I think part of the question was
How are we using it?
basically how the computing power is being provided. I know that has been a question with AI, is, you know, just the energy to actually run it.
Yeah, so SLAC, Stanford Linear Accelerator Laboratories, they are one of our major funders, and they are providing our compute power, along with our partners in France and the UK. I know we are using the cloud to store data. I believe we are using Google Cloud, but I'm not positive, so don't quote me on that. I know our education, our server in our education section is using Google, but I'm not sure if there are different cloud compute services out there. Um, so, but I don't really know a lot more about how AI is being used. I know a lot of researchers now are using AI to fine-tune their research strategies, which I find fascinating. Um, it's creeping into almost every aspect of our life, right? I mean, it's hard to avoid it now, but I'm not really sure how it's applied to data so much.
The question is basically has to do with the data management and trying to figure out how you look at what's there. It's basic, the concern is you're getting a massive amount of data, and how are you or how are the systems going to work to drill down to get at what you need to be looking at within those masses of data to actually get to something useful?
Okay, I'm going to share my screen one more time to show you another picture. Let's see. And I want to talk about brokers a little bit. So every one of these images is going to be scanned within seconds. And okay, let me back up. Before we take pictures of the sky, we're going to make templates of the sky. We're going to take pictures and know where all known objects are, their exact location, their photometry. We are going to know which objects don't ever change in brightness and which ones do. And then we will use these templates to compare when we get an image. And machine learning will compare these templates to each image as it comes in and generate a list of everything that changes and also new detections and an approximate a description of it, in terms of its photometry, its location in the sky, etc. Now, there's a lot of data there, and because there's so much data there, we can't direct it to a lot of places around the world, but we have identified right now what we call full stream community brokers. And these are places that have developed specialized software packages that will ingest our data stream and kick out in any image uh, what everything, a tentative identification of every object. So it might be, a galaxy, a comet, a supernova, a star, and then the information about it. Now, let's say that there's an object that you're interested in. Let's say you're interested in asteroids. And we're going to detect lots and lots of asteroids every night, but you don't want to have to sift through all the data to find the asteroids. You could go to one of these brokers and you could set up a filter on your account. Brokers are software packages, okay? You set up a filter on your account and you say, I only want to see asteroids that are above this magnitude because that's all my telescope can see. And then it will return a list of asteroids and their coordinates, etc. And by the way, we're going to be using the Minor Planet Center to do identifications of asteroids. So we will be working with the system that's already in place. We're also going to be working with AAVSO for variable stars, although that's not all settled out necessarily into details. There are also what we call downstream brokers that are only going to take a small part of the data from a full stream broker and serve that up. So I think like Northern Arizona University, they're only interested in like planetary things. And and so in reality, if you were looking for a certain type of object, you would not go to the science platform and look at an image and try to make sense of it. You would go to a broker and you would query what you'd like to find out, if that makes more sense. You can go to the science platform and make like a cutout of an image that you want to study, because certainly you don't want to have that entire image. But hopefully that clarifies it a little bit. On the topic of amateurs using data, though, our typical limiting magnitude on our images is about 24 for a 30-second exposure. And the stars begin to saturate at magnitude 17. So in effect, anything brighter than magnitude 17, we really aren't going to collect data on because our detectors are saturating. Which means anything that you see brighter than magnitude 17 in your telescope, we're not going to be delivering a lot of data on.
Yeah, the follow-up observation or question was, it sounds like the Rubin will be gathering data, but for people actually using data, that would be coming from downstream sources, so to speak, that have already processed it. Is that how it works?
Yeah, I wouldn't even say processed it. I mean, we will process the data before it goes to the brokers, but what the brokers will do is help us filter it into the type of objects you want to look at.
Great. That answer yours? Yeah, I guess. Anybody else with a question? No, I think it.
I'd like to respond to a
Oh.
few comments in chat if I could.
Sure, please.
One of them, Kim wrote, "Can we see the Milky Way with the naked eye there in Chile?" I have to tell you a funny story about that, Kim. I was just there for the first time ever in November. And I was so excited because I've been working for the observatory for about 8 years and I've never seen our telescope. And so we had 2 nights where we were up at the summit. Unfortunately, the nights were just before full moon. And this is my first trip to the Southern Hemisphere ever. I couldn't even see the Magellanic Clouds because the moon was so freaking bright. And I couldn't see the Milky Way either. The good news is I stayed a week later in Chile to go on vacation. And I was able then to see the Milky Way and the Magellanic Clouds. And that was super sweet for me because I've always heard about them and never had a chance to see them. So that was pretty neat. So, and then there was something else. Somebody had asked about, will Rubin be able to use some form of adaptive optics or laser guide stars? No, we are using active optics. So the difference between adaptive and active, for those of you who might not know, is that active optics relies on just a basically it's like an Excel lookup table. And it says if the telescope is tilted at this angle, you make these adjustments. If the wind load is this, you make these adjustments. But it doesn't correct for atmospheric interference in the same way. However, we do have a plan for that. We can't use a laser system because taking these big wide field images and shooting a laser up there to correct for optics, it just isn't a compatible way to do things. We do have a small telescope next to the large telescope. It's called the auxiliary telescope, or Auxtel for short. And every night, the Auxtel is making measurements of a set of standard stars with a slit spectroscope. And what it does is it compares how the standard star looks that night to how it should look. And that gives us a correction for the atmosphere that we could apply to our images. So we are actively correcting for the atmosphere, but we're not using a laser guide system to do it. So I wanted to mention that because that's a question often asked as well. So, and then the last question from Rick. Once released to the public, will it be possible to choose a region and view a video over time? That's actually, Rick, what we are going to be building in our education and public outreach department. We have a tool called Image Viewer, where we will be able to put these images in and let you do exploration of them, zooming in, either doing guided exploration or unguided exploration, and also having this ability to see changes over time. It's going to be a while before we get that all up and running, but we are planning to have some first iteration of it, some just to look at maybe like the first look images by this summer. That'll be the easy way to do it. I mean, any other way is going to be ridiculously difficult to do.
Okay, great. Thank you. There is another question also. So we haven't had the first look, as you said, but how long is the telescope planned to be operational? Is it going to be a survey telescope all along, or are there plans, maybe thoughts, that in the future it will be repurposed to do something else? The camera changed, maybe?
Mm-hmm. Yeah, so our survey is funded for 10 years from the time we start. I am sure in 10 years' time, there are going to be advances in technology. There are going to be, as we make discoveries with this telescope, we're going to see maybe better ways to adapt it. So I don't know what the future holds beyond 10 years from now. I'm thinking to Ingenuity, you know, the little helicopter that went to Mars, and they expected it to do maybe one test flight, maybe a few more, but you know, at the end of its mission, we were able to repurpose it and do a lot of other things with it. And you know, telescopes typically have a lifetime of way more than 10 years. So I'm sure we will continue on with things, but I don't know what that looks like right now.
Great, thank you. Also, well, your main job is doing a survey. However, you also mentioned collaboration with other telescopes. But can you elaborate more? So, for example, if LIGO finds something, will you be able to pause your survey and quickly capture that? Is that how it works?
Yeah, yeah, and within minutes. I mean, we can get into that algorithm within minutes. We can alter it to pivot. And, you know, we have a number of partners around the world who have follow-up observatories waiting for us to mention something worthy of detection for them. So, and so it will work both ways. Someone might detect something and send it to us for us to investigate. And if it's in our area of the sky, we can certainly do that. Or certainly we will find quite a few interesting things that people will want to follow up on. And we can, right through our alerts, right? Our alerts are coming out continually, 10 million per night. So once you filter the alerts down to what you want to look at, And we could certainly do targeted alerts too to our partners, right? Like, hey, this is really something unusual that you need to look at now. And we can do that.
Okay, great. Thank you. Barbara, any last in-person questions?
Any last questions? Yes, ma'am. The question is there going to be a visitor center in Tucson? Is there going to be one in Chile? Where can we go to check this place out?
Well, yes, and both places. There we have headquarters is not a very interesting place in Tucson. It's a building with a lot of offices. So we do tours every first Friday, but I wouldn't waste my money getting on a plane to fly to Tucson to see our headquarters building. However, um, that we have a headquarters building in La Serena. It's not really a visitor center either, but we will do public tours there once we get up and running. I am guessing because all the other Noir Lab telescopes do that. If you went to Chile, you could sign up for a public tour of Tololo, of Gemini South, Blanco, we do that in Hawaii. You can go on a public tour to see Gemini North. So and we certainly have done a lot of people, we've given tours to a lot of people during construction, but they're primarily like VIPs, government officials, they're not like what I'd say general public. Um, so, but I would not be surprised at all if in the future, once we get up and running, there will be a regular tour schedule in Chile, and that's where I would go to see the telescope rather than a visitor center.
And fun to have something that would be a challenge to like Kit Peak or some of those others in Tucson. Okay. The suggestion here is that people need to get their passports ready.
Yeah.
Any other questions?
There's a question from Rick about how many people will be living on site. Are you talking about on the mountain? Like on the mountain at Chile, I assume?
Most likely, yeah. Probably not the Tucson headquarters.
Yeah, so on site, we have people who rotate up there. I don't think there's anyone permanently that lives there. Most of our people who come up there, we have a whole little installation up there. We have not only the observatory and Oxtel, but we have a cafeteria, we have dormitories, we have other service buildings up there for equipment. But most of our staff ride a bus from La Serena every day. And they get on the bus in the morning that takes them up there. At the end of their shift, they get on the bus and go back. Now, people have shifts all through the night. I mean, so there are dormitories up there and people might stay a certain number of nights, but nobody has a house up there and lives up there. And really there's no town nearby either that people can zip back and forth to. It's mostly people coming from La Serena.
We have a question about how far La Serena is from the observatories.
Well, I can tell you it's about a 2-hour drive, but it's probably not that far in terms of, you can't go like 100 kilometers an hour. So I don't know how many miles it is. I'm sure we could figure that out on Google Maps, but it's less than 2 hours. And about half of it is on pavement and half of it is on gravel. And once you get on the gravel road, the interesting thing is you have to stop at the gate and they give you a GPS unit. And what they're doing is tracking how fast you drive. And if you exceed the speed limit, you can get your driving privileges revoked for driving on the roads up there. Just because we're so safety oriented, it's difficult when there are accidents that far away. So, yeah, about half of the drive, I'd say, is about, between 30 and 40 miles an hour.
We have an additional question here. The question is, at the end of 10 years, would it be possible to have a video playback of all the pictures that have been taken, even if it would take, like over 70 hours or something to view it? But is that something that would be possible?
I don't see why not. I mean, we're looking at probably 800 full color images, so that's not that many. But that would be static images. See, the more interesting things happen. Okay, it's a little complicated, but imagine it this way. If I am taking an image in 2 filters per night, I need 3 nights to get a full color set of filters, right? Now, within those 3 nights, things may have changed. So then if you add it all together, you might not see the change, right? So there are changes on the small scale and changes on the large scale, I guess. And a lot of the changes on the small scale are going to be the ones more interesting. However, the really cool thing about the 10 years is when we start co-adding all those images, we'll go from like magnitude 23 and a half down to magnitude 27 or so. So we're going to see deeper and deeper and deeper and deeper as every year goes by. I've got a bunch of questions here in the chat.
Yes, please.
Let me work backwards. Earthquake protections, yes. We have a pier that is sunk deep into the mountain, and it is supposed to withstand more than a magnitude 9 earthquake. So it's certainly so. We're in the Andes, so earthquakes are pretty typical there, and it's the pier is isolated from the rest of the structure, so we have that vibration protection. Then we also have earthquake safety and evacuation. When we were up there, it's very well marked where you go, what you do but I mean, the funny thing is they said in the event of an earthquake, just stay where you are, shelter in place. If you're in the observatory, just stay there. But there certainly are lots of safety procedures up there. The other question is, how are partially cloudy nights handled? Will photos still be taken? Yes, they will. We're going to suck the marrow out of our ability to take pictures. And we also will be taking images during twilight, because during twilight is the most optimal time to catch near-Earth asteroids. Once it gets totally dark, you might not see them as well. So there are different kinds of science optimized for different times of night, different phase of the moon. So we will be taking pictures as often as we can, with the exception of maintenance periods. And there's another question I don't quite understand. Was any internet enhancement done at the site for data transfers? Are you talking about like an upgrade of, I'm not sure what internet enhancement means. Was it like an upgrade?
Maybe they mean data compression or
Yeah,
something of that sort.
well, at the site in the beginning, there was nothing. It was rock. So everything put in there was brand new, ready to go. And the fiber optic was laid from the summit down. So I know that I'm trying to think. I don't recall seeing any like data processing facility on the summit itself. I know that the first big data processing facility with like all the big computer banks is in La Serena. So I'm not sure exactly how to answer that.
Okay, sure. Thank you. This is just a wonderful talk. Thank you very much for answering all questions. Any last lingering questions, Barbara, or are we ready to adjourn?
There's one question.
Lingering questions here?
There's one question in chat that says, how can the general public contribute? Are you talking about contribute to looking at the data, Kim? Yeah, so well, first of all, we've got this whole program for schools that's targeted mostly at advanced middle school through intro college. All of our investigations use authentic data, and you could look at them tonight if you wanted to. They're all online. We're using proxy data from other observatories until our own data become available. We have 7 different investigations, and they're all on the Rubin Observatory website under the education area. We will have citizen science projects up and running as soon as we have data. We are going to be partnering with the American Association of Variable Star Observers to try to work with amateurs who work in that area, because certainly we are going to make a ton of discoveries and interesting things to look at. So that will be well within the range of some amateur instruments. I think there's going to be a lot of people amateurs in particular, who are going to be interested in asteroid detection. So one of the interesting things we can do is sometimes, this is true of comets especially, right? Or supernovae, you can detect them when they're dim and maybe the amateurs can't see them, but we know they're rising in magnitude. So there will be a point where they do become within the realm of amateur telescopes. And so I think if you're interested in that kind of stuff, maybe detecting a near-Earth asteroid that's coming closer to us, a comet that's moving inward in the solar system, a supernova that's brightening, all those things are possible. And that's going to be working with alert brokers and various other places, I guess, as we develop our systems.
Okay, great. Barbara?
Final question was whether the data is ultimately going to be all within the public domain.
Yep. After 2 years, everything becomes public.
Great. Thank you so much. We've really enjoyed your talk very much and all the information.
Well, thank you. I appreciate being here.
Sure. Thank you very much, Ardis, again. And very much looking forward to have you back maybe in a few years, so that you could share with us all the glory that has come when it's operational. So
look for an
yeah.
event. I'm sure you'll hear about our first look event online, and we're planning a little after party too online.
Great. Thank you very much. And I would also like to thank our attendees, both online and in person. So you could find more about our events at our website at ocastronomers.org. With that said, I wish everybody a great night, and I'll see everybody next month. Bye-bye.